April 16th, 1947, Texas City, Texas. A Caterpillar D7 is pushing into a port that is still burning with steel, timber, and chemical debris piled where the roads used to be. The machine was not built for this, but without it, rescuers were not getting through. To understand why a Caterpillar D7 ended up cutting a path through burning steel and chemical ruin, you have to go back to the industrial geography of Texas City before the blast. In 1947, Texas City was not a quiet Gulf port. It was one of the most concentrated industrial zones on the American coast, a place where refineries, storage tanks, rail spurs, docks, warehouses, and chemical cargo all stood close enough that one failure could reach the next before anyone understood the scale of it. The port handled petroleum products, sulfur, grain, and ammonium nitrate. That last cargo mattered. On paper, ammonium nitrate was fertilizer. In the wrong conditions, confined, heated, contaminated, and packed in bulk, it became something else entirely. The disaster centered on the French freighter Grand Camp, moored in Texas City Harbor and loaded with roughly 2,300 tons of ammonium nitrate. A fire broke out aboard the ship on the morning of April 16, 1947. Dock workers, longshoremen, and firefighters responded as if they were dealing with a dangerous but familiar shipboard fire. Steam was ordered into the hold in an attempt to smother the flames and preserve the cargo. That decision made sense in the logic of cargo protection. It made less sense in the physics that were already taking over inside the ship. As heat built inside the hold, pressure built with it. The cargo was no longer just cargo. It was becoming an explosive mass confined in steel, surrounded by fuel, waterfront structures, rail equipment, warehouses, and workers who were far too close. At 9:12 a.m., the Grand Camp detonated with a force that shattered the harbor front, threw steel and flaming debris across the city, ignited tanks and buildings, and registered with the violence of a battlefield munition on an industrial scale. Entire sections of the waterfront disappeared. Fire companies that had arrived to fight the original ship fire were wiped out almost where they stood. That first explosion was not the end of the emergency. It was the beginning of a new one. The blast ignited nearby oil storage, ruptured pipelines, collapsed structures, scattered cargo, and turned the port into a burning debris field too dangerous for ordinary rescue access. Roads were blocked by wreckage, rail cars were overturned, dock timbers burned, twisted plate steel, splintered lumber, shattered brick, and live fire covered the routes that ambulances, firefighters, and recovery crews needed most. Men were trapped, injured, cut off, or lying somewhere beyond barriers that had not existed minutes earlier. That is where the machine enters the story. The Caterpillar D7 in 1947 was not a giant by later standards, but it was one of the most useful crawler tractors in American heavy work. Depending on exact configuration, a D7 of that era weighed in the neighborhood of 24,000 to 28,000 pounds and carried roughly 80 to 90 horsepower from its diesel power plant. More important than any single specification was what the machine could do under broken ground conditions. Wide steel tracks spread weight where wheeled vehicles bogged or lost traction. A front blade could shove masonry, timber, rail fragments, and industrial debris out of the way. The tractor could move slowly, deliberately, and with enough force to create access where no road remained. On paper, the D7 was a construction machine. In Texas City, after the blast, it became something closer to an emergency engineering tool. The crews facing the wreckage did not have the luxury of a clean plan. The site was still burning. Secondary explosions were possible. Tanks continued to ignite. Smoke reduced visibility. Heat radiated from steel, cargo, and building remains. Some debris piles were stable enough to push, others concealed fire underneath. Some routes looked open and ended at collapsed dock sections, burning cars, or ruptured pipe runs. The machine was not entering a work zone, it was entering a live industrial disaster where the ground itself could not be trusted. Mechanically, the D7 was suited to one part of the problem and vulnerable to another. It could push through tangled wreckage that would stop trucks cold. It could climb over broken surfaces, keep traction in ash, shattered timber, and loose fill, and work without the tire puncture risk that crippled wheeled equipment in debris fields. But the machine was still exposed. The operator sat in an open position with little protection from radiant heat, smoke, or blast-thrown fragments still falling from unstable structures. Fuel, oil, hydraulic lines were fitted, cooling system integrity, air intake, and visibility all became survival issues, not maintenance details. By the time local crews and industrial operators began using heavy equipment to force routes into the port area, the mission had changed more than once. First it was firefighting, then rescue, then access, then survival again, as fires spread through tank farms and waterfront installations. A crawler tractor working in that environment was not simply clearing rubble, it was buying time. Every pass of the blade opened a corridor for stretchers, hose lines, trucks, and men on foot. Every obstruction left in place meant delay, and delay inside a burning chemical and petroleum complex carried its own consequences. The reason a machine like the D7 mattered so much in those hours was simple. Human beings could not lift what the explosion had dropped across the roads. A single beam, a crushed truck, a section of wall, or a pile of dock framing soaked in burning product could stop an entire rescue route. The machine was fighting physics, not just wreckage. It had to break paths through heat, weight, and unstable material, while crews behind it tried to reach the living before the fires or the injuries finished what the blast had started. And the worst part was this: nobody on that first day could know whether the route being opened would stay open. Back at the waterfront, the disaster was still unfolding. By the afternoon of April 16th, Texas City had already crossed from industrial accident into national catastrophe. Fires moved through oil tanks, warehouses, dock structures, rail sidings, and shattered industrial yards with no clear perimeter and no stable front line. The first explosion had killed hundreds outright, but the physical destruction it left behind created a second emergency just as dangerous: a city-scale rescue and access problem inside an active fire zone. In that phase, the Caterpillar D7 was no longer just useful. It was one of the few machines that could still function where roads had ceased to exist. The work was brutally simple in concept and extremely dangerous in practice. The operator had to find a line through twisted steel, splintered timber, broken masonry, ruptured pipe, and burning cargo, lower the blade, and push until something gave way. Sometimes the debris rolled, sometimes it compacted, sometimes it shifted sideways into a new blockage. What looked from a distance like one obstruction was often three layered together: a collapsed wall, a freight car frame, and dock timbers packed beneath it by blast force. On paper, the D7 could move heavy material. On the ground, conditions changed everything. The machine's advantage was traction and controlled force. A truck could reach only the edge of the wreckage. Men on foot could climb it, but they could not reorganize it fast enough to matter. The D7 could. Its steel tracks distributed weight across broken surfaces and gave it purchase where rubber tires would have slipped, punctured, or burned. Its blade could peel back one layer of debris at a time, creating a narrow lane where ambulances, fire apparatus, and hand crews could follow. The operation was slow because it had to be. Push too hard into a hidden beam or pipe run, and the machine could climb onto unstable material and hang up. Strike burning product in the wrong way and fire could spread across the path just opened. Then, just after 1 a.m., on April 17th, the margin disappeared. The freighter High Flyer, which had been moored nearby and also carried ammonium nitrate along with sulfur, detonated after burning for hours. The second explosion tore through a port and city that had already been wrecked by the first. Structures weakened the day before were finished off. Debris fields were reset. Fires expanded again. Whatever access routes had been partially cleared near the waterfront were threatened, blocked, or erased outright. What had been a rescue corridor 1 hour could be an impassable burn zone the next. That second blast explains why machine access mattered so much in the aftermath. Texas City was not dealing with one explosion and then cleanup. It was dealing with a chained industrial disaster in which each new fire and detonation changed the terrain. The D7 and machines like it were fighting a site that would not stay still. Mechanically, the problem was this. The crawler could survive rough ground, but it could not survive unlimited heat. Radiant heat from tank fires could cook the operator long before it destroyed the machine. Air intakes could draw smoke and ash. Cooling systems were under constant strain at low speed, high load work. Steel debris could foul track frames, jam rollers, or wedge under the machine. Burning liquid product introduced a danger that no crawler tractor was designed to solve. If fuel fire spread under the tracks or around the machine's belly, the operator had seconds, not minutes, to back out. That is why these operations depended as much on judgment as on horsepower. The operator had to read the debris field the way a quarryman reads rock or a swamp hand reads ground. Which pile would move cleanly? Which one concealed fire? Which route actually led somewhere useful? Where was the machine still working construction logic? And where had the job become a survival decision? In disasters like this, the machine entered the crisis long before the crisis became visible. As routes were forced open, the consequences became immediate. Fire crews could move hose and equipment deeper into the damaged port. Trucks could approach areas that had been cut off. Recovery teams could reach bodies and survivors trapped beyond collapsed structures. Industrial crews could begin isolating damaged sections of the site, pushing wreckage away from key lines and access points before another ignition made the whole area unreachable again. The D7 was not ending the disaster. It was making response physically possible. The human cost around it was staggering. Official death counts eventually reached nearly 600, with thousands injured, though the exact number has long been debated because so many bodies were destroyed, never identified, or counted imperfectly in the chaos. Entire fire companies were lost. Dock workers vanished where they had stood. Families across Texas City were searching hospitals, morgues, temporary aid stations, and debris fields for the missing. In that setting, a bulldozer blade clearing a lane through the port was not an abstract image of heavy equipment at work. It was part of the machinery of recovery in one of the deadliest industrial disasters in American history. The site is quiet now compared to what it was that week in April 1947. But the consequences are not. The Texas City disaster changed industrial safety law, chemical handling practices, emergency planning, and legal doctrine in the United States. It became one of the defining case studies in how dangerous cargo, poor hazard understanding, and dense industrial geography can combine into mass casualty. It also revealed something more basic and more physical. After the explosion, before the reports, lawsuits, and reforms, somebody still had to get through. That is why the machine still matters. The Caterpillar D7 did not cause the disaster. It did not stop the explosions. It did not save the port. What it did was more specific and, in its own way, more important to the hours that followed. It pushed into a place where ordinary vehicles could not go. It turned rubble into access. It gave rescuers, firefighters, and recovery crews a path into a landscape that had been violently rearranged by fire, steel, and shock. The machine is gone. The lesson remains. In industrial disasters, survival often depends not only on warning, planning, and firefighting, but on whether someone can physically reopen the ground between the living and the damage. In Texas City, that job fell in part to a crawler tractor built for dirt work and forced into catastrophe. If you appreciate machine history told at ground level, subscribe. And if you've worked demolition, refinery maintenance, port cleanup, or post-fire debris operations, tell us what stands out to you here. Because Texas City would not be the last time an American disaster had to be entered first by steel tracks and a blade.